Welcome to this lecture. This is lecture number 3 of week 5. In the previous lecture, we have discussed about the law of large numbers, where we are looking at a given sequence of random variables and corresponding limiting behavior of the sample means. There we had also formulated the results in terms of the partial sums, but in most cases we will be interested in the sample means behavior. We have seen two types of laws of large numbers. One was the weak law, where we considered convergence in probability, and in another formulation we looked at almost sure convergence, and those we called as the strong law of large numbers. In this lecture we are going to see applications of these results. So without further delay, let us continue the discussion using the slides. Alright, so again we set up the notation. We are given a probability space, and on this probability space we are given a sequence of random variables. Now let us say we are given that the weak law of large numbers holds for the given sequence of random variables, but then the weak law is essentially suggesting that take large enough number n, so essentially taking large enough sample, the corresponding sample mean based on this random sample will be close to the expectation or mean of the given distribution. And here in the weak law of large numbers, the closeness will be determined in terms of convergence in probability. So for large enough small n, if you are taking very large number of samples, then the corresponding sample mean is essentially converging to the expectation. So that is the closeness we are interested in. So that is essentially getting guaranteed if the weak law of large numbers hold. And in practice, this observation can be used to find the approximate value of the expectation of a distribution. So if you do not know the expectation of the distribution, take large enough samples, many samples from the distribution, take the sample mean, that will be standing for an approximation to the expectation, provided of course the expectation exists, and this is essentially getting guaranteed by the weak law of large numbers. So as long as you can ensure that the weak law of large numbers holds for your sequence of random variables, you can get the corresponding sample mean converging to the expectation. But this concept or this principle has very nice applications. So let us look at a very simple situation where we are given a sequence of random variables IID, independent and identically distributed, with the common distribution given by Bernoulli P for some p between 0 and 1. But now here these sequence of random variables can be interpreted as a sequence of coin tosses with probability of success, which is essentially obtaining a head in a toss, as the number p. So this is essentially repeated tossing, and depending on whether you observe a head or a tail, you assign the value 1 or 0 with probability p and 1 minus p. Now in this case you are having a IID random variables with Bernoulli random variables. Here the relevant integrability conditions hold, so you can appeal to the weak law of large numbers. And here as part of the weak law of large numbers, we will conclude that the sample mean converge in probability to the expected value, but this value is exactly the number small p, and the convergence in probability essentially tells you that for all epsilon positive, the limit of the probability that xn bar, the sample mean, away from the number p by this number epsilon, that event has probability going to 0 as n goes to infinity. So that is the interpretation of the convergence in probability. Now this essentially supports the intuitive notion that by tossing a coin very large number of times, we can essentially make a educated guess about the value of p. So a priori, if you are given a coin, we do not know what is the value of p, you repeat the tossing, and then what you end up with is that the number of heads out of the total number of tosses, that ratio essentially gives you an approximate guess about this number p. So whenever you are working with this unknown number, you can make a guess by using this weak law of large numbers. And more generally, you can further extend this idea to looking at the relative frequency approach of defining probabilities. Remember, in a random experiment, what you do is that you can appeal to the relative frequency of observing certain events, and you can try to assign the probability based on the relative frequency, and that is the working methodology that we want to justify using the weak law of large numbers. So, let us see. So, suppose we are given some event E in some random experiment and we repeat a random experiment n times. What we are going to observe is that whether this event E occurs or not in each of the trials that we are running. But now, given the jth trial where j is running from 1 to n, we will associate a random variable to be 1 if the event occurs and 0 otherwise. Then you observe that by the nature of a random experiment, these random variables x1 up to xn must be independent and identically distributed, and moreover the common distribution is actually given by Bernoulli. So, the random variables are taking 0 and 1 values, and the probability of getting 1 is exactly the probability of observing the event E. So, therefore, this number p is actually the probability of the event, but now if you do not know what should be the probability of the event, this p is unknown. Now, in this case, if p is unknown, what we can do? We can look at the observed relative frequency of the number of times when the event E has occurred, and this is exactly given by this quantity, that the summation xj's is the exact number of times where the event E has occurred, and divide by n to get the relative frequency. But now, the weak law of large numbers tells us that this is a good enough approximation for this unknown value of p, which is the probability of E when your n is large, and the approximation is in the sense of convergence in probability. Alright. So, let us see another interesting interpretation or calculation involving the sample means. So, here what we do? We start with IID random variables xn, but we assume additional integrability which are in L2. Now, look at the sample variance which we denote by Sn squared. So, just to be careful, we are no more writing Sn to be the partial sums, we are thinking of Sn as the corresponding sample standard deviation. So, now we are having this formula for the sample variance which is given by this. Remember, we are scaling by 1 by n minus 1, just make a note of this. Now, here what we are going to be interested in is for large values of n, how does the sample mean as well as the sample variance vary for large n of n. Alright. So, let us see. So, by the weak law of large numbers, if you look at the sample mean, it will converge in probability to expected value of x1. But now, you can look at the square function, this is a continuous function on the real line, and you can appeal to continuous mapping theorem which we have discussed in theorem 1 of week 4. This will tell you that convergence in probability can be lifted through this continuous mapping to this quantity, that xn squared, that will also converge in probability to the square of the limit, and this is still convergence in probability as n goes to infinity. But now, our interest is in the sample variance that we have looked at. Now, this can be rewritten in this algebraic formulation. So, this verification I leave it to you to check, but this is a very standard verification that the earlier description of Sn squared that we have taken, as long as you expand the terms using binomial theorem, that can be simplified and written in this formulation. Note that this has two terms. The second term we have a good idea about because we have the sample mean squared, but what about the first terms? So, here you see that xn squared, these are also IID random variables, but original xn's were in L2. So, therefore, xn squared are actually in L1, and in particular these are IID random variable with common mean now given by expected value of x1 squared. Now, here we can appeal to the weak law of large numbers for this sequence of IID random variables, and we can claim that the corresponding sample mean for the xi squared, so this should be j here, this is a typo. So, the corresponding sample mean, so you are dividing by n here, that in probability should converge to expected value of x1 squared. So, this is exactly the application of the weak law of large numbers to this new sequence of IID random variables. But now we appeal to the algebraic properties of convergence in probability that was discussed earlier in theorem 4 of week 4. So, here you go back to the formulation of Sn squared that we have seen earlier. You see that n by n minus 1, that quantity goes to 1 as n goes to infinity. So, these quantities go to 1. Now, multiplication by such kind of real valued sequences we can think of as degenerate random variables, but since they are converging to 1, so we are also having convergence in probability, and in convergence in probability the products are also allowed. So, therefore, in particular the second term here, if we look at the right hand side, that will converge to expected value of x1 whole square. So, that is what is happening as a consequence of the algebraic properties of convergence in probability. On the other hand, the first term we have shown that here this term here by the weak law of large numbers converges in probability to expected x1 squared, but now we are scaling them by these quantities n by n minus 1, but these are also going to 1. So, again by appealing to the algebraic properties we finally claim that Sn squared must converge in probability to this quantity, which is expected x1 squared second moment minus the first moment squared, and this is exactly the variance of the original random variables. So, therefore, what we have ensured is that Sn squared, the sample variance, converges in probability to the variance of x1. This is essentially the consistent estimator for the variance of x1. Alright. So, we have actually used here the fact that limit of n by n minus 1 is equal to 1, and these are being treated as degenerate random variables and which are converging to 1 in probability. But now, as long as you can show that Sn squared is approximating variance of x1 in the sense of convergence in probability, you can again appeal to the continuous mapping theorem and appeal to the square root of the functions, and then what you again can get is that Sn, which is now the sample standard deviation, this will now converge in probability to the square root of the variance, that is the standard deviation of the original random variables. So, this is a nice application of the weak law of large numbers and using the algebraic properties of convergence in probability. Now, we look at another interesting application of this type of laws of large numbers. We start with a sequence of IID random variables which we denote by yn. Now, what we do? We fix a real number small x and look at a new sequence of random variables. So, what we are doing is that we are looking at the event whether yns are less or equals to x or not. If that is the case, we assign the value 1, otherwise we assign the value 0. So, these new random variables xn superscript x, these are 0 1 valued random variables, but since xn x only depends on yn, we immediately get that xn x for every fixed value of x will again form an IID sequence of 0 1 valued random variables, and therefore, it is a Bernoulli random variable, and then we are interested in the value of p. So, p is actually the probability that this new random variables take the value 1, but it takes the value 1 only when yn is actually less or equal to x, and therefore, it can be written in terms of the common distribution function capital F that we have used here. So, therefore, the value of small p that we are using is this capital F of evaluated at small x. So, note that here we are fixing my small x and doing all of our calculations, but now for that fixed value of small x, look at the empirical distribution functions defined in this way. Note here that the empirical distribution functions by definition are certain random variables, and for each sample point small omega, these are given by these quantities. So, there what we are looking at are these xj's which are 0 1 valued, and we are essentially counting whether the yns are greater or equals to x or less or equals to x and that kind of a quantity, and we are essentially scaling by n, essentially again our relative frequency of the similar kind of a situation. Alright. Now, here we will drop again by our notations that we are going to drop all this small omega. So, fnx is a random variable for each fixed x as well as n, and here we note that we can appeal to the strong law of large numbers that we have discussed earlier and claim that fn of x that will converge almost surely to the expected value, which is exactly the f of x, and this holds for every fixed value of small x. So, in fact, if we go back to the proof of the weak law of large numbers that was discussed earlier in the proposition 1, we actually can show that since all these random variables in question, the xn's, are 0 1 valued, therefore, they are all in L2 and all that, and the variances are uniformly bounded, you actually can show that fnx actually converges to f of x in the L2 space of convergence, and this holds for every fixed value of x. And in particular, L2 convergence also implies the improbability convergence. That is how we had proved the weak law of large numbers, the first version of it. So, what we are having is that the sequence of empirical distribution functions, they converge to the actual distribution function in the almost sure mode, in the improbability mode as well as in L2. But of course, L2 mode of convergence implies L1 mode of convergence. So, this was discussed earlier in week 1, please go back and check, and as a consequence the expected values will also converge to the corresponding expected value, which is this deterministic quantity f of x. But in fact, in this situation what is happening is that the expected value for every fixed value of n, that is, can be computed in this way. So, this is 1 by n of the sum of the individual expected values, but here xj's, these quantities are taking the value 1 with the probability f x and taking the value 0 with the probability 1 minus capital F x. So, therefore, the expected value is exactly this. So, therefore, for each value of n and x, the expected value is actually f of x. So, the limit of course, as we have pointed out in the previous statement, definitely holds. But let us look at the L2 convergence setup, which we have discussed earlier in the weak law of large numbers version. So, we are just going back to the same proof, we compute the variance of these quantities. But now we can also recenter it by this number, and that is going to give us, using the independence of these random variables, the sum of the variances and scaled by n squared here. And if you simplify, you will end up with this quantity. These are the common numbers because all the random variables are IID. So, since this number is fixed, as n goes to infinity, we will get that the variance are actually going to 0. So, that is the consequence of the proof that we have discussed for the first version of weak law of large numbers, that we have first shown the L2 convergence, which implies the convergence in probability. And in fact, in a later lecture we are going to come back to this exact same formulation, and we are going to discuss an improved version of this almost sure convergence. So, here to point out what we have obtained, the almost sure convergence, here this holds for all x, but this holds for separately for each x. In particular, the almost sure convergence will come with a null set, and the null set now, as per our construction, depends on the choice of small x. Later on, what we are going to see is that this null set can be in fact chosen independent of the choice of small x. That is what we are going to discuss in a later lecture. Alright. And finally, let us look at another interesting versions of these laws of large numbers. But now we have been discussing so far are the cases when either the random variables are in L2 or in L1, meaning they come with certain integrability conditions. Now what we look at is that we will drop the integrability assumptions. So, suppose this happens that the sequence of random variables are IID, but expected value of x1 is plus infinity. Now, as per the measure theoretic interpretation of this expectation, what we are going to get is that the x plus that random variable will have the expectation to be plus infinity, but the negative part of the random variables will have finite expectation, and that is when we can define the expected value of x1 to be the difference between these two quantities. So, if the first quantity on the right hand side is plus infinity, second quantity is finite, then the difference becomes infinity. So, this is the quasi integrability setup that we are interested in. Now first let us assume the cases when all these random variables, the negative part of it is 0, meaning the random variables, original random variables are non-negative. So in this case what we do is that we fix some number capital M positive and we look at the truncation, meaning that we truncate the non-negative random variables xn to the cases when xn is taking less or equal to m. That is the case we are looking at. So whenever xn is taking the value strictly greater than capital M, this product that we are looking at, the truncated value, that will be 0. Now these truncated random variables are always dominated by capital M, and in particular these are all having as many moments as we want. Now for this let us look at the corresponding averages of the sequence of partial sums. So here what happens is that the lim-inf, if we want to compute it, this will be greater or equal to the lim-inf of these quantities, because Sn is made up of x1 up to xn by n, but individually all these terms are greater than the corresponding truncated values, and that is where we get the inequality. So therefore lim-inf will also satisfy the same inequality. But let us concentrate on the truncated random variables. Here you note that in fact the limit exists. So therefore this lim-inf on the right hand side is actually a limit, and that is coming from the strong law of large numbers setup, because these random variables are uniformly bounded by m. They are first of all non-negative and bounded above by m, and therefore here you get all moments being finite and all required conditions are getting satisfied. So you can appeal to the Kolmogorov's strong law of large numbers that we have discussed earlier in theorem 4, and you will end up with that this limit is in the almost sure mode of convergence, and it will go to the expected value of x1 truncated up m. But consequently what you can get is that we are having a lower bound of this lim-inf that we have started off with on the left hand side, and the quantity of interest is this Sn by n, the lim-inf of that. Since this is greater or equal to these quantities, expected value of x1 truncated at capital M, we can let m go to infinity. So we can take capital M to be some positive integers and let it go to infinity, and again we can essentially end up with this almost sure convergence by looking at all the intersections of the sets of full measure. Another way to look at it is that for each fixed value of positive integers capital M, what we can do, we can pick out the null sets, look at their union which is again a null set, throw it out on the complement of that big null set, we are getting these calculations. So here again almost surely what we get is that lim-inf of Sn over n, that is greater than this quantity, and you can take let m go to infinity here, that quantity is actually expected value of x1, because the truncation, as long as you let m go to infinity, you are going to approximate the original value only. So this is essentially an application of the monotone convergence theorem. Please check this. But now expected value of x1 in this special case is actually infinity, right, and therefore what you end up having is that lim-inf of Sn over n is equal to expected value of x1, which is plus infinity. But in general for any sequence the lim sup is greater or equals to lim-inf, and therefore that is also plus infinity. So hence the limit holds, which actually is plus infinity, which matches with the expected value of x1 in this case, and this is the almost sure convergence that we are having. But now in the more general case where now the xn's are taking real values, so positive or negative values, mixed possible situations, there we have to look at separately the positive part of it and negative part of it. And now here our assumption is that the original random variables xn's have plus infinity as its expectation. So the corresponding xn plus, if you look at that sequence, that is going to form a IID sequence. Again if you are going to look at the negative parts of them xn minus, they are also going to form a separate IID sequence. Now separately look at the corresponding laws of large numbers for the positive parts as well as the negative parts. So for the positive parts, the expected value that we have now is plus infinity, and using the first part of our discussion, this limit will be plus infinity that we have just established. But now in the negative part case, we are having that the expectation is actually finite, and therefore we can appeal to the usual strong law of large numbers and we will end up with this limit. And therefore if you subtract it just using the algebraic properties of almost sure convergence, we are going to get that the subtraction is essentially going to give you Sn over n, and the limit of that is now plus infinity, and that holds in the almost sure convergence framework. So, we can in fact make similar arguments if we start off with expected value of x1 to be minus infinity. In that case, the positive part of it will have finite expectation, the negative part of it will have infinite expectation, and we can appeal to similar arguments and we can get the relevant results. So, in this lecture we have seen some nice applications of the laws of large numbers, and specifically the question involving the convergence of the empirical distribution functions will be revisited in a later discussion. We stop here. Thank you.